Hi everyone, thank you very much for attending this session at AsyncAPI Conf. Today I'm going to talk about one of my favorite topics, which is the usage of specifications and contracts to ease the delivery of complex systems. I love the theory behind specifications, but I love even more when they can be used in a pragmatic way to speed up things. In the event-driven space, there's all these questions about AsyncAPI and CloudEvents that are two recent specification initiatives. People asking if they are competing, if they'd better choose one or the other. And I'll try to explain in this session that I think that they're in fact complementary and can be used together. You'll see that it does not make things harder, and that the Microcks tooling, the open source project I'm working on, can help you bootstrapping your AsyncAPI plus CloudEvents projects. But first thing first, let me introduce myself. So my name is Laurent Broudoux, and I am wearing many hats. On daytime, I am wearing a red one, being a solution architect at Red Hat, working on cloud-native technologies. And at night, I am putting on my open source contributor suit, and that's why I'm here talking to you today. Daily, I help organizations moving to cloud-native architectures and practices, integrating these new paradigms with their legacy. I have a special focus on everything related to distributed systems, API and specifications, Kubernetes, enterprise integration patterns. These are my favorite topics. And all the time, I'm a happy dad of 5 and a gardener. This has its importance for the end of the talk. So today, events are everywhere, and they are the foundations of event-driven architecture. And we know that their benefits are huge. To sum up, it's all about decoupling. It's a question of temporal decoupling, allowing processing of events in real time or a long time after their creation. It's about technical decoupling, allowing different technologies to be used to be integrated together. And it's about runtime decoupling, adding resiliency and retry in case of failures, allowing non-blocking exchanges, enhancing the scalability of the system. But we know now that the rise of event-driven architecture often comes with many challenges if this type of architecture, it's all brand new for you. The first one is about the technology choice. This is a very broad and very hard topic. It's impossible to address in 45 minutes. We are not that ambitious. But I think it's important to take some assumptions on this one, as it may have consequences on the two others. In fact, I truly believe that it's impossible to pick up a single technology. Technology choice will always make you consider different use cases, as the event-driven landscape is very broad. So you'll probably end up with a solution for modern event streaming and analytics use cases, something like Kafka, Pulsar, or NATS. A solution for safely and easily exposing data streams to the outer world, like WebSockets or Socket.io. And some other solutions like AMQP, JMS, MQTT, for example, if you consider integrating with the legacy, or if you deal with IoT use cases, for example. So there is no silver bullet yet. And the reality is that you'll have to use different technologies to address this diversity. So we can mark this first challenge as solved, but it brings a lot of constraints that are inputs for looking at how to describe our events and ensure we share a common understanding on what's going on. There are also inputs for a third item on how to work efficiently as a team. This is because we probably don't want to have drastically different ways of working depending on the technology only. Again, this last one is very ambitious, and I only give you insights on how to quickly bootstrap autonomous development teams by breaking dependencies. So let's dive into the specifications landscape to check how to describe events. Things are perfectly clear on the way to go for request reply based communications using REST APIs. OpenAPI specification is the winner. But on the event-driven side of things, things aren't that clear. We have AsyncAPI on one hand and CloudEvents on the other. There are still emerging initiatives and people asking, are they competing? Are they tackling the same problems? Do you have to choose and then give up some benefits from the other spec? The fact that both of them are so-called specifications doesn't make it clearer, even if they are different beasts. So we'll try to answer those questions in a few minutes, and for that we'll have to dig into what they are and what pain they address. I suppose that most of you today already know AsyncAPI, so I'll try to be concise, but it's interesting to get back to the sources of each initiative to really understand that in fact they tackle different issues. So let's start with AsyncAPI. What is AsyncAPI? Obviously, you know that it is an open source initiative. It has joined the Linux Foundation, and its goal is to improve the design and the specification process of event-driven architecture by defining contracts. It is made to describe event-driven APIs that may be using different messaging protocols. In fact, it has an abstract part that is generic, whatever the protocol, and it may include specific protocols bindings informations such as destination names, quality of service levels, and so on. It can be seen as a sister specification to OpenAPI. It's very similar, and it may also use JSON schema under hood to specify the abstract part that is related to data. The very nice thing about AsyncAPI is that it allows definition examples. That is one of the parts we can heavily rely on to address our third challenge. If we have a look at the pain it tried to solve, it's really the one of users and consumers of event-based systems. Let's say you have an application, a system, some devices, whatever, on the left that present eventing capabilities. It may emit or process asynchronous messages. As a user, and without AsyncAPI, you always struggle to find information about those capabilities. What are the endpoints and protocols? What are the security policies? What is the expected data format? How can I validate my message? And so on. And AsyncAPI is here to answer that. Its goal is to allow an easy discovery and comprehensive understanding of the eventing capabilities of a system. For that, it implies the same principle as for REST APIs, so that event endpoints become truly managed APIs. In the AsyncAPI ecosystem, we find a complementary protocol binding specification, because AsyncAPI does not enforce any particular protocol, but the contract you write may embed specific protocol stuffs. AsyncAPI by itself is not a software library to install, but there is an extended tooling provided by the team and the community, so that there's this, for example, super nice online studio for editing. There is different code generators for different languages and frameworks. There is documentation generators as well as tooling for mocking, simulation, and testing. If we look at the anatomy of a AsyncAPI contract, we'll find some elements that really look like those from the OpenAPI specification. We first have an info header containing identification information like name, version description, as well as owner's contact, for example. Then we can find a servers block where you'll get the list of brokers that are offering access to the event-driven API. It may contain also different environments, protocols, and security informations. The most important part of AsyncAPI spec comes from the channel items definitions. Similar to the paths in OpenAPIs, channels allow us to define endpoints and operation on these endpoints. Operations are of kind publish or subscribe, and are holding message definitions, where a message is clearly defined using headers and payload data schemas informations. At this point, you can choose to embed your own schema or to reuse existing ones that have been defined using JSON schema or Avro schemas, for example. The spec also allows you to define components like schemas, traits, message definitions that you may reuse across different channels or operations. Okay, so now we have a broad understanding of AsyncAPI. Let's look at Cloud Events. What is Cloud Events? According to the CloudEvents.io website, it's also a specification for describing event data in a common way. And from that, we can immediately deduce that the scope of Cloud Events is more narrow than the one of AsyncAPI. Cloud Events' focus is to provide common formats to guarantee interoperability across systems and platforms. In fact, it defines a minimal set of events metadata and serialization rules for that. Cloud Event specification is organized through the Cloud Native Computing Foundation serverless working group, as the initial work around Cloud Events was triggered by the need to deliver invocation events to serverless and function as a service frameworks. So they try to put a standard for that in order to ensure the portability of functions and workloads. If we look at the pain it tries to solve, we can see that Cloud Events tackles very different problems from AsyncAPI. Let's say you still have an application, a system, some devices that are emitting events. We suppose that at the end of the day, this event should result in some new analytics or new data recorded into a database or data lakes at the right. And for this, you have to trigger some processing in the forms of traditional application, microservices, or even serverless or function workloads. And in the complex world we are living, this is very probably involving many kinds of middleware components. These components realize filtering, routing, aggregating, transforming, or brokering of events to their destinations. So this is exactly the problem Cloud Events try to solve. How to ensure that these middleware components are able to route and to deliver events in a very efficient way. This is more and more important as we are all adopting edge or hybrid cloud strategies. If we look at the ecosystems of use case in Cloud Events, we can see that as it addresses very common needs, the number of use cases is really large. So we can find Cloud Event solutions that are simply general purpose event brokers. That is what is providing the majority of cloud providers. But Cloud Events is also very well suited for event-based workflow automation. The use of the standard by the orchestration engine guarantees its interoperability. We also obviously find a lot of serverless or function as a service frameworks. The most famous being Knative, that brings a lot of components to implement Kubernetes native middlewares able to filter, broker, or transform events. And finally, we can also find a lot of specialized or vertical solutions that have been made Cloud Events friendly, so that the events they are producing can be later reused in any Cloud Events compatible pipeline. This is true for IT-focused solutions like Debezium or Falco, that is addressing security, for example. But it is also true for business-oriented solutions like commerce tools, for example. If we now have a look at the anatomy of the specification, you will see that it comes in different independent parts. The core specification of Cloud Events is a very tiny one, as it just defines the minimal set of metadata that every event should have. Nothing really new or exotic in here. It's just 4 mandatory attributes and 4 optional ones. So you've got attributes for defining the kind of events. It's the spec version and the type attributes. You've got attributes to clearly identify the event. This is the ID attribute. You've got attributes to define the context the event was sent out. It's the source or the subject and the time attributes. And you finally have attributes to define the shape of the carried event data. That's the content type and the schema attributes. The core specification also defines different locations or modes for transporting these attributes. The binary mode is adapted to existing messages, as it recommends putting the metadata attributes outside of the payload within the protocol headers. The structure mode defines a wrapped message format where the metadatas are into the payload, wrapping the carried data. It's indeed very useful if you do not have a pre-existing message format. In my opinion, the names of the content modes are particularly ambiguous, as you can carry out binary encoded data using the structure mode, and you can also carry out text encoding data using the binary mode. I think that raw and enveloped would have been better terms, but that's how it is. Aside from the metadata definitions, there's also specifications for defining serialization details regarding the event format, JSON or Avro for the moment, and the transport protocol. Nothing more to say here, but let's look at an example. It will help to visualize things. So this is an example of a JSON encoded structured cloud event that uses the HTTP protocol. Imagine you have pulled a GET endpoint and you received that HTTP response. The first thing to notice in structure mode, you see that Cloud Events has its own content type. It's application/Cloud Events plus JSON. Then you see that the metadata are at the root of the payload, and then you find the carried data with a data property. This property could be of any type, and this content type can be specified within the data content type attribute. Here in the example, you can see that we are transporting XML data, in fact. Now we can have a look at the binary content mode, and you can see that the metadata of Cloud Events are now serialized as HTTP headers using the C- notation. The data is the one of the payload, and the response content type is simply the one of the data. You can find the content type header having the text/XML value. The binary content mode is clearly my preferred way of doing things, as it allows to add Cloud Events capabilities to existing events, but also because I think it leads to more performant implementation of the middlewares involved in routing. With the binary mode, the middleware just have to consider the headers, and they can totally ignore the payload while they are doing their job. Okay, so we had a walkthrough of both specifications. Now let's summarize things. Obviously, AsyncAPI and Cloud Events are sharing common features. We saw that they are both protocol agnostic. They are also very friendly to different encoding. JSON and Avro and their schemas are supported. And there is also ongoing efforts in the community to make this list larger with, for example, the addition of protobuf to the list. Hence, we can conclude that both specification is able to support most of the technology choices and is also able to integrate with legacy systems. This is of great importance as we outlined it when dealing with the first IDEA challenge about the technology choice. Now, let's see the differences now. In this table, I summarize how I see the differences and then come to the conclusion that there is no overlap between the two specifications. Both are certainly very useful when dealing with large systems. They have different goals to provide a description of API capabilities on one side, to ease interoperability on the other. And for that, they are focusing on different parts. AsyncAPI helps you define channels to be used for applications and let you choose your message format. CloudEvents provides you useful common metadata to define the event's message format. You can also see that the people who are describing or using both specifications are also pretty different. And you'll certainly need to address all of their concerns. In an organization, the adoption drivers behind AsyncAPI are mostly the API owners, because they want to ease the discovery and the understanding of the API to ensure its reuse and success. Thus, the application developers are the consumers of the AsyncAPI document describing the API. And that is because the AsyncAPI document is mostly used at design time and build time. Choosing to use AsyncAPI or not, in fact, it has no real impact on what will be transported on the wire. And on the other hand, people most concerned about using cloud events are the platform architects, as it will allow them it will allow their product to easily integrate with the ecosystems, even for the use cases that they haven't thought about yet. The middleware developers will then be interested in the metadata values to deliver efficient middleware components. So you see, different concerns, different people, but all of them must be addressed. And luckily we are able to combine the two specs to get all their benefits. So let's see now how to combine them together. The combination of both can be achieved thanks to AsyncAPI extension mechanisms. Though, depending on the content mode you choose for your cloud events, you will have to choose different mechanisms. On the left side, we describe how cloud events fit in the AsyncAPI contracts of your event structure, event-driven API using the structure mode. Because AsyncAPI is leveraging JSON schema and its extension capabilities, you'll just have to reference the cloud events core specification and then locally describe the data attributes only. On the right hand, on the right side, we now describe the binary content mode. Maybe you remember that in binary mode, the metadata is serialized as message headers. So here, where we are using the trait extension mechanisms, that allows us to simply include the protocol headers in the AsyncAPI spec. You'll keep the raw payload definition within your AsyncAPI document. The nice thing about these two ways of doing things is that we don't bother about cloud events definition. It's just a matter of adding a reference to the spec and then focusing on the carried data definition. As it's still a bit theoretical for the moment, let me show you some code. And as said in my introduction, I'm also a gardener, and this is the back of my garden, and I use it to introduce today's use case. As I spend a lot of time at home lately, I wanted to set up an inhabitant sensor system. And I wanted a smart one, able to recognize different kinds of animals, cats, hedgehogs, squirrels, and emit events when entering or exiting the frame of the camera. So let's suppose we have this raw data represented here in JSON, containing the type of animal, a detection score, its pet's name, and the detection timestamp. The first thing would be to CloudEvent-ify it. So we define a type to make the difference between entering or exiting the frame. This is the bullet one. And you can see that we also have a lot of context information. CloudEvent does not help defining the data, so we have to define our JSON schema outside and provide it into the data schema property. And finally, you can see in the data attribute the carried out business data of our events. It helps interoperability, but does not help describing in a formal way my architecture. So now let's see how we can use AsyncAPI to specify a contract without Cloud Events for the moment. This is an extract of my AsyncAPI definition for my animal sensor. And you first see the different channels definitions here. And as we have no mean in business data to make the difference between in and out events, we define two different channels that may result on Kafka topics, for example. As AsyncAPI leverages the JSON schema, it's now possible also to define and embed the description of the carried data in a formal way. We have the animal message payload description. So we now have a formal description of the data format, allowing the developer to learn the different channels and to understand the data structure. But it lacks context. And that's why we'd like to add the Cloud Events to the mix. First, we structure the content mode. Okay, so we now have to change our AsyncAPI file, and you can see on the first bullet that we just have to add a reference to the Cloud Event spec here in the message payload. We can refine different types of events, okay, and we can locally define now the carried out data schema. So within the animal data type, we'll find the same properties definition as before. Let's now see binary content mode, and to spice up things, we can use an Avro binary encoding on the data this time. So the first thing will be to define an Avro schema describing a new animal record type. This has to be saved into a specific Avro schema file. So this is my Avro record definition. And now looking at the AsyncAPI document, you'll see that we have changed the content type of the message to binary Avro, and we are referring to an Avro schema. We have added a reference to a Cloud Event trait to include all Cloud Event specific headers. And finally, define our payload using the previously defined Avro schema. One important thing to notice here, don't be confused with the Microcks reference when specifying the trait. This is not specific to the Microcks tooling, this is just the name of the repo where the trait is stored. I hope that this example allows you to reconnect dots and make things clearer. You'll see them in action in tooling in a few minutes. So far, we've dealt with 2 of 3 challenges, and we saw that both AsyncAPI and Cloud Events should be considered in the picture when describing events, alongside with JSON schema and Avro, of course. Let's now see the third challenge, how to efficiently work as a team with events. And as stated before, this is a very broad topic, and I just explained how to set up an efficient bootstrap for your project. An important thing in starting every project is the feedback loop, how to ensure that what we design is of value for the people who are using it. In the context of an event-driven system, there's the additional difficulty of having access to the infrastructure. It's better to not have to wait for the sensor to be plugged and to detect animals in the garden to start developments of processing and giving feedback. So that's the problem we are going to address now. And specifically to address it, we are going to use one very nice feature of AsyncAPI and contract design in general. It's the ability to specify examples. Often we neglect the importance of examples. Most of the time we let some tools generate them, and finally all the string properties have a value of string, all the number of properties may have a value of 1, and so on. But I do think that it's a best practice to pay a great attention to the examples, because they should represent real life scenario. And when carefully chosen, examples can be real good illustrations of business expectations, and thus they can be later used as executable specifications. So basically, that's what we are doing with the Microcks tooling. We turn the examples from AsyncAPI into actionable simulations to realize mocking. And then later we are able to reuse them as datasets to realize testing. Let me say just one word on Microcks. Microcks is a project I started some years ago, and it reached the 1.4 release last month. It's an open source Kubernetes native tooling. It provides a tooling for API mocking and testing. We are tackling 3 specific concerns when dealing with API with Microcks. The number one is to shorten the feedback loop, because API are products. People are adopting agile methodologies, so they want to get feedback very early in the process, and they want to be able to rapidly evaluate new changes. So this is the main driver. The number 2 is how to parallelize developments, because once we decide what is the API to develop, we absolutely want to avoid any bottleneck. We do not want to have developers consuming APIs to wait for backend. In our case, wait to have the animal sensor plugged in the garden. Number 3, it's how to validate implementation. This point is getting richer when you are releasing numerous versions of your API, and you will need to be sure that your implementation is still backward compatible. So Microcks is able to realize contract testing with each and every changes. The big differentiator in Microcks is that it's doing this for all kind of APIs. Event-driven APIs, of course, but also REST APIs, legacy SOAP web services, or gRPC services. So in a nutshell, Microcks proposed 2 different use cases. The first one is about simulation or mocking. It integrates with your source of truth, your Git repository. It discovers and generates live endpoint in seconds, so the API consumers can start playing with the API as it was live, as it was already developed, without writing a single line of code. Okay. The second one is about ensuring compliance. So once your team has started, you can plug in Microcks within your favorite CI/CD pipeline runner, and within each and every commit, you check if changes break compliance on your API version contract. Okay, so let's finish our talk with a rapid demonstration of Microcks on our garden sensor use case. First things we can see here is our AsyncAPI definition that has been loaded into the AsyncAPI Studio Online, and we'll find here our animal sensor structure API. This is the structure version of this API. And one thing we have started with is to add examples to this API. So here I have defined 2 examples right here, and I have just defined them using YAML structure. Okay. In the payload of these examples, I will have the different cloud events metadata informations right here, and the wrapped business data of my message. Okay. Within examples, I surely want to put some static informations, like for example, the type, the kind of event that it is dealing with. But in order to be effectively used, I can also use some specific notations right here, using a double mustache notation to specify, for example, that here I would like to have a unique identifier, and here using the now function I would like to have a specific timestamp. Okay, this specific notation is indeed understood by Microcks, so that later on we will be able to produce some dynamic values within the example. And this is very nice for the different consumers that will play with this example, so that they have a dynamic data and, with a rich data sets. Okay, so let's now imagine I'm happy with this design and I can save everything into my source of truth, into my Git repository. The next step is now to import everything into the Microcks tooling. Here I have the Microcks tooling running, okay. It can act as a central repository for all your API and services definitions, but the repository is empty for the moment, okay. So you can manually add new definitions by uploading contracts and specifications, but you can also import them from your source of truth, from your Git repository, using an importer. Importer will allow you to define a scheduled import or to define webhooks, so that with each and every design revision, Microcks will be updated with the latest changes. So let's start with the structure version of this API, and we will activate it into Microcks. So it will normally discover this API and yes, populate the repository. Right here we find the animal sensor structure API. Okay, we have access to the AsyncAPI contract and documentation. Okay, and we can see the detail of operation, the subscription, when you've got animal detections. And just right here, you'll see that Microcks has found two samples, two mocks that were defined within our specifications. Microcks is able to manage different protocol bindings for your AsyncAPI, Kafka, MQTT, or WebSocket. Kafka is currently the default one, so just after having imported the API definitions, Microcks has created for us a new Kafka topic for this API, and each and every 3 seconds it will publish new messages on this topic. So as an API consumer, I can just start playing with the topic that is managed by Microcks, and each and every 3 seconds, if I use the animal sensor structure API topic, I will retrieve new events that are dynamically produced by Microcks. So we have not yet written a single line of code. Just from the specifications, Microcks allows you to bootstrap your feedback loop. Okay, and we can check that each event right here has a unique identifier and a generated timestamp for each and every message. Okay, so very nice. Let's now check the binary version of this API and the particularity of the binary version. So in the binary version, I want to use Avro binary encoding. So I have had a reference to an Avro schema within my AsyncAPI file, as demonstrated before during the presentation. But when you use Avro in a Kafka ecosystem, you want the Avro schemas to be published and accessed through a schema registry. The schema registry will allow your API consumer to dynamically retrieve the Avro contract so that they are able to deserialize the data carried out by the event. So connected to Microcks, I have a schema registry. I'm using the Picario registry that is for the moment empty. And we are going to activate this API in Microcks. So, like previously, it has detected this API, the binary version. You can see that it has also found the Avro schema right here, and you have details on the operation as well. So this time, the different cloud events metadata is mapped, is projected onto the different headers. Okay, and you'll have the Avro data of the sample that is represented as JSON right here. It's better to display JSON here because it can be read by humans. Like before, Microcks has created a topic for us, okay, but also it has dynamically published the Avro schema on the registry. So now as an API consumer that is dealing with Avro, I can directly reuse the topic that has been generated for me by Microcks. So this is the binary topic I will use, but this time I specify that the value is Avro, binary Avro, and I will have to use the registry to dynamically retrieve the schema. And you can see this time that, yes, that's it. Each and every 3 seconds I still receive new events. I have all the cloud events related metadata that are provided within the headers by Microcks, and the Avro that is put here and deserialized and displayed as JSON for ease of read. So you can see that by setting up Microcks, you can very efficiently set up a feedback loop and bootstrap your development team so that they can start developing in parallels, even without writing a single line of code. Let's get back now to the presentation. Okay, so let's wrap up things. We addressed the 3 EDA challenges we previously identified, adding a mix of examples and Microcks tooling to the previous one to ensure quick bootstrap of your project. Of course, it required a lot more to guarantee efficiency during the whole project life. Finally, if you would need to recall just one thing, these are the key takeaways of my talk today. I hope having succeeded in demonstrating that it's not a matter of AsyncAPI or CloudEvents exclusive choice. Both are very useful to design and implement your event-driven architecture. AsyncAPI defines the whole EDA space, and CloudEvents ensures interoperability. Both are very useful to address the concerns of the different people in the organizations: API owners, API consumers, platform architects, or middleware experts. And luckily, they can be combined easily, and they can also be simulated very easily thanks to Microcks. This ensures the setup of the feedback loop in your project, and this ensures also the setup of the conformance validation. Okay, because the examples you have put in your specification with the schemas information may be reused later by Microcks to ensure that the real data that is produced by your application is in conformity with this contract. Final word on Microcks: we are an open source project. We welcome everyone to come, to share ideas, to contribute. We want it to be purely community and user driven, so try it, give us feedback. Do not hesitate connecting and chatting with us on our Zulip chat. Many thanks for your time attending this session today, and see you later. Bye bye.